Hey everyone, we're going to start a new chapter today. This is chapter 10, and it is called Cosets and Lagrange's theorem. So we'll start off with the definition. And so let's let G be a group and H a subgroup of G, right? So we start off with a group and then a subgroup. Oh, and we need an element too. So let's say H there, and let's take an element, little g in capital G. Now the set, which we write as little g times H. And by definition, this is the set of all things, all elements of the form little g times little h, where little h runs through all of capital H. So this set has a name, right? This is called, so this is the left coset of, yeah, okay, so the left coset is what it is, but it's the left coset of capital H containing little g. So the idea is you have your subgroup H, take all of the elements of capital H, hit it, multiply by those elements on the left by little g, right? And that the set of all those elements is called the left coset. There's also the right coset. So the set, which we would write as capital H times little g. So that will be the set of all elements of the form little h, little g, where little h runs through all of capital H. This is the right coset of capital H containing little g. All right, so we have left cosets and right cosets. And so let's start with an example. And the example, I want to work with D4. And so I'm going to write out the elements as, so remember D4, that's the dihedral group. This is going to be the symmetries of a square. And it has the rotation, so we'll have row 0. We'll have row 1, row 2, and row 3. So row 0 is the identity. That's the 0-degree rotation. Row 1 is 90-degree rotation counterclockwise, and then row 2 is 180. Row 3, that's the inverse of row 1, so it's 270-degree rotation. And then there's going to be, what symbols do I use here? Mu1, mu2, delta 1, and delta 2. So mu1, mu2, delta 1, delta 2. And let me draw a picture of what we have here in terms of the elements. So we have 4 lines of symmetry like that. And mu1 is going to be the vertical flip, right? The vertical reflection. So there's mu1. Mu2 will be the horizontal reflection. And then delta 1 and delta 2 are going to be the diagonal reflections. Delta 1 is this one. And delta 2 is that one. And then, of course, we have the 90-degree rotation counterclockwise, so that's row 1. And so row 2 is going to be row 1 squared, and row 3 is going to be row 1 cubed, right? So that means rotate 270 degrees counterclockwise. Now, I want to take a subgroup. I want to look at cosets. And so let H consist of the following elements. So it's going to be row 0, row 2, mu1, and mu2. So you can check that this actually is a subgroup. It's easy to check that we've got a subgroup of D4. And so let's create some cosets here. So let's look at row 1H. So what do we get here? I'm going to multiply on the left-hand side by row 1. And so first, if I do row 1 times row 0, we get row 1. Row 1 times row 2, that's going to be row 3. Row 1 times mu1 gives me delta 1. And then row 2 mu2, oops, row 2, why did I just write that? Row 1 times mu1 is delta 1, and then I also get delta 2. All right, so you can check. As you multiply each of these elements in order by row 1, you will get each of these elements in order. And I also want to look at the right coset, so that would be H row 1. And what we'll get is row 1, row 3, delta 2, and then delta 1 in order. All right, so in particular, if you do row 1, if you do row 1 times mu1, you get delta 1. But if you do mu1 times row 1, you get delta 2. All right? But in the end, notice what we get is the same set. It's written, they're listed in different order, so let's just say, though, note that row 1 times H is equal to H times row 1. So the left coset is equal to the right coset. Let's look at another example. So it'll just be another subset. Sorry, subgroup. Oh, and I should point out before I move on. So H is a subgroup, but this coset right here is definitely not a subgroup. It doesn't even have the identity in it. So in general, cosets are not subgroups, right? In fact, the only time that you'll get a coset that's a subgroup is if you do the identity times H. Okay, so let's do another example. So now my subgroup is going to be K, and it's going to consist of row 0 and delta 1. All right, so this is definitely a subgroup of D4. And then I want to do, I'm going to do mu1, right? I'm going to do the cosets corresponding to mu1 or containing mu1. So mu1 times K. So let's see now, I'm going to multiply each of these elements on the left-hand side by mu1. And we will get mu1, and I think it's row 3. Yeah. All right, so the left coset, mu1, and row 3. And then I also want to do the right coset, so K mu1 is going to give us mu1 and row 1. Right, so what that means then is mu1 times delta 1 is row 3, but delta 1 times mu1 is row 1. And so in this case, so note here, what we have is that the left coset mu1 times K is not equal to the right coset K times mu1. So sometimes you get equality, sometimes you don't, and it'll be a question, when exactly do you get equality, and why is that, and why might that be interesting? Okay, so there's our first examples of left and right cosets. One thing to be aware of, so let's say, I guess notation. So in general, right, so this is the standard notation, G times H, right, is the typical notation for cosets. But if G is abelian, and H is a subgroup of G, and I need another element, little g is an element of capital G, then we typically denote the coset using added notation. So this denotes the left coset. So typically, and we don't have to get too specific, but when the operation is addition, we will usually write the coset like this. And similarly, the right coset, so similarly for H plus G. So for example, so let's say in Z, let's take, I want to take the subgroup 6Z. So in Z, I want to look at, let's say compute 0 plus 6Z, 1 plus 6Z. So note, we've got an abelian group. The operation here is addition, so I'm writing it using additive notation, but it means exactly the same thing, right? So what it means, and I guess I should have been a little more clear what was happening here. So now you'll have all objects of the form G plus little h, where h runs through all of capital H, right? That's what the left coset is going to be because the operation is addition. So there's really nothing changing here. It's just recognizing that the operation is addition. So my cosets here, 0 plus 6z, 1 plus 6z, 2 plus 6z. In fact, I'd like to write them all out. And I kind of gave away the answer here. It turns out that there are exactly 6 cosets, right? 0 plus 6z, 1 plus 6z, all the way down to 5 plus 6z. And when I say compute, I just want to write them out. So 0 plus 6z, that means the set of all things of the form 0 plus little h, where h lives in 6z. Well, let's see. The elements in 6z are multiples of 6. And so if you take all the multiples of 6 and add 0 to it, well, you just get the multiples of 6. So that would be dot, 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 minus 12, minus 6, 0, 6, 12, dot, dot, dot. So in fact, 0 plus 6z, that's just 6z itself. 1 plus 6z. So what I want to do now is I want to take all the elements of 6z, which we can see here, and add 1 to it, or 1 to them. So dot, 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 negative 11, negative 5, 1, 7, 13, dot, dot, dot. Right, so there's 1 plus 6z. 2 plus 6z. So now I take all the elements and add 2 to them, and we'll get dot, 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 minus 10, minus 4, 2, 8, 14, dot, dot, dot. And you know, I mean, I kind of gave it away. So let's just, I'm going to put dot, dot, dot here. I don't want to draw every single one of them. Let's do, so dot, 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 and then over here, I'd like to write down 5 plus 6z. So 5 plus 6z, that's equal to, so let's see, I take all multiples of 6 and add 5 to that. So if I add 5, I'll get minus 7, and then minus 1, and 5, and 11, and add 5. Add 5 gives me 17, dot, dot, dot. And then if I tried to keep going, what if I wrote down 6 plus 6z? Well, if you add 6 to multiples of 6, what do you get? You get multiples of 6. So nothing changes here. This is exactly the same as 0 plus 6z. And if I wrote down 1, if I did 7 plus 6z, what you'll find is that you get exactly 1 plus 6z. So this starts to repeat itself, right? 7 plus 6z is exactly the same as 1 plus 6z. And this pattern will continue. So it turns out that when it comes to left cosets, there are exactly 6 of them. 0 plus 6z all the way down to 5 plus 6z. And then the pattern starts to repeat. So our first result, and I want you to notice what's happening here. If you look at these cosets right here, there's absolutely no overlap between the cosets. All right? If you're a multiple of 6, you are not the same as a multiple of 6 that has had 1 added to it, which is not the same as a multiple of 6 that's had 2 added to it. And so as you go down the line, what you'll find is that this is a disjoint collection of sets, and if you take them all together, right, they start to repeat afterwards, but if you take all of them together and take the union, you get every single integer. Every integer, this is kind of a division algorithm thing, right? Every integer is either the form multiple of 6, or 1 plus a multiple of 6, or 2 plus a multiple of 6, all the way down to 5 plus a multiple of 6, right? Listing the possible remainders that you get when you run the division algorithm. And so here's our first result from this chapter. So theorem 10.1. So let's take a group. So let's let G be a group. And we need a subgroup. H, subgroup of G. And then 2 parts to this theorem. So the first one, the set of left cosets of H forms a partition of G. And then the same thing for the right coset. So the set of right cosets of capital H forms a partition of capital G. Right? So when you take cosets, it chops up the group into a bunch of non-overlapping pieces. Now, for the proof, this proof, or the idea behind this proof, really is going to give us a way to think about how to work with cosets. So you do want to pay attention here. So I want to define a relation. So let's define a relation, call it tilde, on G by, let's say on capital G by A tilde B, if and only if A inverse B is an element of H. Now, okay, so I've defined this relation, but I use the symbol tilde kind of as a hint. This is going to be an equivalence relation. And remember, every time you have an equivalence relation, you have a partition and vice versa. Partitions and equivalence relations are one and the same. And so what we're going to do is we're going to show that this is an equivalence relation, so we'll go through the steps, and then once we have an equivalence relation, we're guaranteed to have a partition on our set G, our group G, and then we'll need to show that the corresponding partition is exactly the set of left cosets. So when we show that tilde is in equivalence relation on capital G. So first we'll do reflexive. Let's label this. Let's see, so reflexivity would mean that A is equivalent to A, and that's going to be true if and only if A inverse times A is an element of H. So since A inverse times A equals the identity, H is a subgroup, so it definitely contains the identity. So since A times A inverse equals the identity, which is element of H, we see that A tilde A, right? So A is related to A. Now for symmetric, so let's take a couple of elements. So let's let, and you know, now I feel bad. I should have started my sentence a little bit better here. On my reflexive, I really wish I would have written let little a be an element of capital A. And then for part B, for the symmetric part, so let's let A and B be elements of capital A with, why am I saying capital A? Sorry, that capital A there should be a G, and that one should be a G right there also. So let A and B be elements of G, where A tilde B. So what does that mean? So then what that means is that A inverse times B is an element of H. Okay. All right, what do we do now? Well, I need to show that B is related to A, which means I need to show that B inverse times A is an element of capital H. And maybe you can see what to do, right? H is a group, which means it's got inverses. So in particular, A inverse B, right, has to be an element of H. So, now what we have is B A inverse, which is equal to the inverse of A inverse times B. That has to be an element of capital H. Remember, to find the inverse of a product like this, you reverse the order and negate each element. So if I reverse the order and negate, right? Oh, whoops, whoa, I just wrote that ridiculously. So now B inverse A is equal to A inverse B all inverted, and that's definitely an element of H. All right, so therefore, B tilde A. And now for transitivity, so now I'm going to choose three elements. So let's let A, B, and C be elements of G, where A tilde B and B tilde C. And then what do we need to do if we want to prove transitivity? We need to show A tilde C. Well, okay, so let's write down what this means. So then A inverse B is an element of H, and B inverse C is an element of H. Once again now, since H is a subgroup, it's closed under multiplication. So we can say it follows that. So since it's closed under multiplication, if I multiply this element of H times this element of H, we get an element of H. So it follows that A inverse C, which is A inverse B times B inverse C, is an element of H. Thus, tilde is, well, no, sorry, I don't want to say it that way. Thus, A tilde c. So we've shown that we got an equivalence relation on G, and now, well, let's say it like this: since tilde is an equivalence relation, on capital G, the set of equivalence classes, right, G mod tilde, this is a partition of capital G. So what I need to do now is show that the equivalence classes correspond directly to the cosets, right? That's what we're trying to show, is that the cosets form a partition. And what we know from general nonsense in Math 248 is that the set of equivalence classes, this G mod tilde, is a partition of G. All right, so to show that the left cosets form a partition, it suffices to show that show that what? That for each little a in capital G, the equivalence class of A is equal to the left coset AH, right? So then what we would have is each equivalence class corresponds to a coset. That means that the cosets form a partition because the equivalence classes form a partition. Okay, so I want to show equality, right? So to do so, let X be an element of the equivalence class of A. So then what does that mean? That means, all right, so that means that X tilde A, and so then X inverse A is an element of H. Is that the way I want to write it? Let me just check something here. X inverse H. Oh. Yeah, actually, what I wrote here is true, but to make it look better, I want to write it a little bit differently. So, sorry. So then, A tilde X, and so, A inverse X is an element of capital H. Yeah, that looks better. So it follows that A inverse X is equal to little h for some little h in capital H. And now hopefully you can see what I'm going to do. By multiplying both sides of this equation by little a, so now X is equal to A times H. I just multiply both sides by little a, which is an element of the left coset A times H. So what did we do? We started off in bracket A. We ended up in A times H. So therefore, bracket A is contained in A times H. For the reverse direction, so now given, now let's let, I don't call it y, little y, be in A times H. Then, so let's see, what does that mean? That means that y is equal to A times little h for some little h in capital H. I'm really not doing anything high-powered here. I'm just using the definition of coset. Okay, so if y equals A times H, it follows that, so let's see what that means is it follows that A inverse times y is an element of capital H. Why is that? Because A inverse times y is equal to little h, which of course is in capital H. And so, A tilde y. Therefore, let's see, if A tilde y, that means that y is equivalent to A, which means that y lives in the equivalence class of A. So therefore, y is an element of bracket A. And we conclude that. So what did we do now? We started off in the left coset and we ended up in the equivalence class, so we can conclude that AH is contained in bracket A. So now we have inclusion in both directions. That's exactly what we needed, right? And so that completes the proof. All right, so let's say it now. I'll actually write a concluding sentence. So now we have that G mod tilde, the set of equivalence classes, is equal to the set of cosets, little g times capital H, where little g runs through all of capital G. And so, the set of left cosets is a partition of G, and the reason, because the set of equivalence classes is a partition of G. The proof of B is basically the same, so the proof of B is similar. That's worth you going through and figuring out what the appropriate equivalence relation is in the case that you're dealing with right cosets instead of left cosets. Okay, so that completes the proof. And I want to make a couple of remarks. And these remarks, every time I teach this class, I mean, cosets are a tricky thing to wrap your head around. And we're going to do some fairly advanced things with cosets. So you want to be able to work with cosets. You want to be able to understand what this whole coset business means. And so these remarks are designed to ensure that you do understand. If you understand and remember, more particularly, if you remember what I'm writing down or what I'm about to write down, this will enable you to work cleanly with cosets. And this is one place where students just have difficulty. So I want you to remember and pay attention and remember to what I write down for these remarks. So remarks. Okay, so the first remark, so from the proof of 10.1, we have, well, so we showed that cosets form a partition, and with partitions, if you have two pieces of a partition, they're either equal or they're disjoint. So this tells us we see that left cosets are either equal or disjoint, right? So that's important. And then the question becomes, how do you decide whether two cosets are equal? And this is the key. This is where students sometimes a lot of students get stuck because they don't remember this fact right here. So we'll say, in particular, the left coset A times H is equal to the left coset B times H, right? Remember, they're either equal or this disjoint. So this is true if and only if A inverse B is an element of capital H. And I could have done it so I could have done it the opposite way. So we'll say another way to do this, if and only if B inverse A is an element of H. So this is absolutely crucial. If you want to understand how to work with cosets, you're going to need to be able to decide whether two cosets are equal or not. This is how you do it. This is the way to do it, right? And we're going to need to be able to do this. And the same thing for right cosets. So let's write it down for right cosets. HA equals HB if and only if A B inverse is an element of H, if and only if B A inverse is an element of H. We tend to work with left cosets more often than right cosets, so I kind of focus on this one, but both of these are things that you need to be able to do, right? So this is crucial for your understanding of how to deal with cosets. Now, I'll just say, call this remark number 2 here, so so part 2, in general, left cosets and right cosets are not the same, right? So in general, we saw an example earlier when I was doing that example with the dihedral group. So in general, the left coset AH is not equal to the right coset AH. One place where you're guaranteed that they are equal, so we'll say, of course, if G is abelian, then AH, the left coset, equals the right coset for all little a in capital G. That's not the only time that it happens, but if you're in a abelian group, you're guaranteed left cosets and right cosets are always exactly the same. Yeah, let's see how long I've been going. Yeah, okay, that's plenty. So I think we'll stop here. That's kind of weird for me to be talking that closely. All right, we'll stop here, and we'll see you next time. All right, bye.